Welcome to the Deep Dive. We sift through technical sources to pull out the core knowledge you need. Today, we're really getting into the fundamentals of ultrasonic testing, specifically the physics behind it all, how the waves get going, how they travel, and really importantly, how they interact with materials.
Yeah, this is absolutely foundational stuff. If you're an NDT, getting these basic math and physics concepts down, well, it's not just theory. It's key to knowing how ultrasonic waves carry energy through a solid. Understanding that helps you correctly find a flaw. We're really defining the disturbance itself.
Today's Deep Dive is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description. Okay, so let's unpack this a bit. We talk about UT signals all the time, but what is a wave, really, in this context?
Fundamentally, a wave is just a disturbance. Think of it as a localized physical shift of material particles away from where they normally sit, their equilibrium position. The crucial thing is that this disturbance carries energy through space over time. But the material itself, it doesn't travel along with the wave. It just sort of oscillates back and forth right where it is.
Right. And when we model this, even though the UT signals we see are these complex bursts, we always seem to start with the simplest version, the sine wave. That gives us the core properties, doesn't it?
Exactly. It's the building block. To describe any wave, really, you need three main properties. First up is frequency. That's simply how often the wave oscillates, how many cycles it completes in 1 second. We measure that in hertz. You can also think about it using the period, which is just the flip side, the time it takes for one single complete cycle. So if the period is, say, half a second, the frequency is 2 hertz, 2 cycles per second.
Okay, so frequency is about the timing, the oscillation in time.
Right.
Then the second concept gets at the wave in space. That's the wavelength, right?
Correct. Wavelength is the physical distance between two identical points on successive waves, like from one peak to the next peak. It's basically how long the wave physically is as it moves through the material.
And then the third piece ties time and space together, phase velocity.
Yeah, phase velocity. That's the speed at which a specific point on that sine wave, like its peak amplitude, travels through the material. If you know the wavelength, how long it is, and the period, how quickly it cycles, well, speed is just distance over time. So velocity is wavelength divided by period. It tells you how fast that individual wave component is moving.
Now, here's something really key for NDT, I think. Our sources always stress that UT uses non-periodic pulse waves. Short bursts, not those nice continuous sine waves. So how does the simple sine wave math apply to the complex pulse we actually see on our screen?
That's where the sort of mathematical elegance comes in. Any complex pulse, even a short burst of energy, can actually be represented as a sum, like an infinite sum of individual simple sine waves, all with different frequencies. You add them all up at any given point in time, and they combine to create the exact shape of the pulse you're measuring. It's called a group.
Okay, and that leads to something really interesting. The difference between the speed of those individual sine wave bits and the speed of the whole energy package. Phase speed versus group speed.
Absolutely critical distinction. The phase velocity, like we just said, that's the speed of each individual sine wave component making up the pulse. But the group velocity, that's the speed of the overall pulse envelope. It's the speed of the actual packet of energy you're tracking across your scope.
And if we lived in a perfect physics textbook world with perfectly linear materials where stress and strain have that perfect straight line relationship, then those two speeds would be the same.
That's the ideal theoretical case, yes. But, and this is crucial for real-world testing, real materials aren't perfectly linear elastic. They just aren't. Because of these slight nonlinearities, those individual sine waves making up the pulse, they actually all travel at slightly different phase speeds. And since each component travels at its own speed, they start shifting relative to each other. They recombine differently as the pulse travels.
Wait, so you're saying the actual shape of the ultrasonic pulse changes as it goes deeper into the part?
Exactly. That's the phenomenon called dispersion. It means the material is dispersive. The group velocity and the phase velocity aren't equal anymore, and this has a huge practical impact for you. If the pulse shape changes, maybe that sharp leading edge you use for your neural timing measurement gets smeared out or looks different later on. That can really mess with your timing measurements and make it harder to accurately size a flaw just based on how long the sound took to travel.
Wow, okay. That really brings the physics down to the shop floor, doesn't it? It's not just theory. So that naturally takes us from the wave itself to how these waves travel through the bulk of a material. Body waves. Let's start simple. Isotropic materials, things like most metals, where the properties are the same no matter which direction you look.
Right, for plain body waves traveling through isotropic solids, there are really only two main types that can propagate through the bulk. First, you have longitudinal waves. We denote their speed as $. In this mode, the particles of the material vibrate back and forth, parallel to the direction the wave itself is traveling.
So pushing and pulling in the same direction the energy is flowing, like a compression wave.
Exactly. They're often called pressure waves or dilational waves because they cause these little zones of compression and rarefaction or stretching. And critically, because this parallel motion is the most direct way to pass energy through a solid lattice structure, longitudinal waves are always the fastest wave mode in that material.
Okay, fastest mode. And the second type, transverse waves.
That's right. Transverse waves, or shear waves, with velocity $. Here, the particle disturbance is perpendicular at right angles to the direction the wave is propagating. Think of shaking a rope up and down. The wave travels along the rope, but the rope itself moves vertically. This motion involves shear deformation, meaning no local volume change happens as the wave passes. And the fundamental rule is always, longitudinal velocity is greater than transverse velocity. $5 VT-TLS. Always.
And that speed difference can be pretty dramatic looking at the data. Like an aluminum-uranium alloy has a longitudinal velocity around 6.35 kilometers per second. That's fast. But compare that to water, where $5 is only about 1.49 kilometers. It really shows how much quicker that disturbance travels through a stiff, organized metal structure compared to a fluid.
Exactly. And for most common metals, that simple two-wave model of longitudinal and transverse is enough. But you mentioned things like advanced composites or certain alloys. Those can be anisotropic.
Right. Anisotropic means properties depend on direction. How does that mess things up?
Well, it gets significantly more complex. Because the elastic properties change depending on direction, think about wood grain, or fiber direction in a composite, these materials can actually support three distinct body wave modes. There's one quasi-longitudinal mode and then two different quasi-transverse modes, each with its own velocity.
Okay, 3 modes instead of 2. But what's the real practical headache for the NDT tech?
The big headache is that the group velocity, remember that's the direction the energy packet actually travels, can diverge from the phase velocity, which is the direction the wave crests seem to be moving. So if you're inspecting something complex, maybe a single crystal turbine blade, you might aim your probe straight at where you think a flaw is based on geometry. But the energy packet itself, the group velocity, might actually get steered off course by the material's internal structure. It might bounce off a sidewall differently than you expect, or just travel in a slightly different direction.
Whoa, that sounds like it could make finding the exact location of a flaw really tricky. How do people even deal with that?
It takes deep knowledge of that specific material's properties. Often, you need computer simulations or careful calibration with known reflectors to map out how the energy actually flows, not just where the phase velocity points. It's why inspecting complex geometries or anisotropic parts needs really specialized procedures, specific probe angles, and sometimes multiple tests from different directions.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
Okay, so moving on. Whether we're dealing with longitudinal or transverse waves, isotropic or anisotropic materials, a huge part of UT is figuring out what happens when that wave hits something, a boundary, a flaw, a discontinuity.
Right, and one factor is just the size of that something compared to the wavelength we're using.
Exactly. If the discontinuity, say, a big crack face or a large void is large compared to the wavelength of the sound hitting it, you get a nice clean reflection, almost like a mirror. The angle of reflection equals the angle of incidence, makes the return signal predictable and strong. But if the flaw is much smaller than the wavelength, think tiny pores or inclusions, the wave doesn't reflect cleanly. It scatters. The energy bounces off in all directions kind of randomly. So the signal that comes back is much weaker, more spread out. Detecting that scattered energy tells you you're likely dealing with small stuff.
And then there's the case where the wave hits a boundary between two different materials. That's where angles change and Snell's law comes into play.
Precisely. When you hit an interface between two different materials, some of the wave's energy reflects back, but some of it transmits into the second material. This transmitted wave is refracted, it changes direction. Snell's law gives us the math to figure out that new angle. Essentially, it relates the angles and the wave speeds in the two materials. The wave sort of bends to try and keep its speed component along the boundary consistent.
We also need to remember that signals get weaker as they travel further. Attenuation. Why does that happen? What's the practical effect?
Yeah, attenuation is just the signal losing strength. It happens because of various energy loss mechanisms within the material. Things like grain boundaries scattering some energy, internal friction converting mechanical energy to heat, basically elastic effects. This energy loss isn't linear. It's typically measured by an attenuation coefficient, and it causes the wave's amplitude to decay exponentially as it travels further. That's why for really thick parts or materials that are highly attenuative, like some composites or cast metals, you need powerful transducers and maybe lower frequencies. Otherwise, the signal just fades away into the noise before it gets back.
Okay, let's shift gears slightly. We've talked about waves going through the material. What about waves that stick to the surface? Surface waves.
Right, the most common one we encounter is the Rayleigh wave. These waves are interesting because their energy is really concentrated right near the surface, typically only penetrating about one wavelength deep. And the way the particles move is pretty complex. It's not just back and forth or side to side. It's an elliptical motion, kind of rolling backwards relative to the wave direction, like watching a buoy bobbing on the ocean.
And a key thing about them is speed. They're always slower than the bulk transverse wave, right?
Yeah.
$5 is less than $5.
Always slower, yes. And that has a practical use too, because higher frequency Rayleigh waves are confined even closer to the surface due to attenuation effects. You can actually tune the frequency of your probe to investigate different shallow depths. Very handy for finding surface-breaking cracks.
And what happens if we're doing, say, immersion testing, where there's water coupling the probe to the part?
Then you get what are called leaky Rayleigh waves. Because that surface particle motion has an up and down component, it efficiently transfers energy into the fluid it's coupled with. This energy leaks out of the solid into the fluid at a very specific angle called the Rayleigh angle. This leakage can actually cause the main ultrasonic beam in the fluid to shift or distort. That's the basis for phenomena like the Schoch effect, where the reflected beam seems displaced.
Okay, interesting. Now, one last really crucial bit, especially for angle beam testing, the critical angle phenomenon. Let's focus on what happens when a transverse wave hits a free surface, like the edge of the part, at a specific angle.
Right, the critical angle. Let's call it the theta TC for the transverse to critical angle. This is the specific angle of incidence where the reflected longitudinal wave, if it were created, would theoretically have to travel exactly parallel to the boundary at 90 degrees. Since we know longitudinal waves are always faster than transverse waves, there must always be some incident angle for the transverse wave where this theoretical 90-degree longitudinal reflection would occur. That's the critical angle.
So what's the practical upshot? What happens as we approach that angle and then go past it?
Okay, so below the critical angle and the incident transverse wave hits the boundary, the physics demand that it generates both a reflected longitudinal wave and a reflected transverse wave. You get mode conversion. It has to happen to satisfy the boundary conditions, how the stresses and displacements behave right at the surface.
Both L and T waves bounce back, but once you tilt your incident transverse wave beyond that critical angle.
Once you exceed theta 2 things change dramatically. Mathematically, a real propagating reflected longitudinal body wave simply can't exist anymore. It would violate the physics. So to satisfy those same boundary conditions, two things happen instead. First, the energy that would have gone into the longitudinal waves now generates a specific type of reflected surface wave. It's distinct from the Rayleigh wave we just discussed. And second, the reflected transverse wave now has a reflection coefficient of -1.
-1. So its amplitude is the same, but it's completely flipped. A 180-degree phase shift.
Exactly that. A perfect phase reversal upon reflection. It's quite a complex interaction. And it's why choosing the right angle for angle beam probes is so critical. You need to know which modes are being generated and reflected to interpret the signals correctly.
This complexity really highlights how much the initial wave type matters, doesn't it? Because there was one reflection case you mentioned earlier that sounded much simpler.
Absolutely. The simplest reflection scenario involves what's called a transverse horizontal wave, or SH wave. In this case, the particle vibrations are still transverse, perpendicular to propagation, but they are oriented parallel to the reflecting surface horizontally. When an SH wave hits a stress-free boundary, it reflects only as another SH wave. The reflected amplitude equals the incident amplitude, and crucially, no mode conversion occurs. No longitudinal wave is generated. It's the cleanest, simplest reflection possible in solids.
Okay, so wrapping this all up, what does this mean for someone learning UT? We've seen it's way more than just sending out a ping. It really hinges on understanding these subtle, sometimes counterintuitive physics. Particle motion, the difference between phase and group speed, how angles and materials dictate reflections and conversions, all the way from simple back and forth motion to those complex rolling surface waves.
The big takeaway for you, the listener, has to be this. These fundamental rules of wave propagation are your essential toolkit. Things like Snell's law for angles, or the fact that real materials are dispersive and change the pulse shape. You need these building blocks.
Yeah.
Because if that pulse does change shape as it travels, or if the wave converts from, say, transverse to longitudinal when it hits a flaw, you, the technician, must recognize what's happening physically to correctly figure out that flaw's size and where it is. Without understanding this underlying physics, the signals on your screen are just, well, squiggly lines.
Before we wrap up, if you enjoy these deep dives and want to support us in continuing producing this content, please buy us a coffee by scanning the QR code on the screen. It's an easy way to support our work and the subscriptions needed to create this content. And a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.